Yeah, we are going to start. Wait a minute. Narasimha, you can take start. You can.
Okay. Good evening, all. So it's my pleasure to introduce Professor Nuno Freitas from ICMAT Madrid, and he will be today he will be speaking in the year-long program on triangular groups, Bailey information, and modularity. And he will be discussing or informing us about the overview of modularity of elliptic curves or total real fields. So, Nuno, the floor is yours. Thank you.
Thank you for the introduction and for the invitation. So today I'm going to speak about modularity of elliptic curves over total real fields. I'll give a overview of the results that have been achieved so far. I will explain the main points of how these theorems are proved. The modularity of elliptic curves over total real fields comes naturally after the proof of modularity of elliptic curves over the rationals. So this is a very well-known result. It was a great achievement of Andrew Wiles when he proved that all semi-stable elliptic curves over Q are modular, and the objective of doing this at the time was highly motivated by the resolution of Fermat's last theorem. So that's also well known, and it's the statement that there are no solutions in the integers to the equation x to the n plus y to the n plus z to the n equals 0 if we take these integers a, b, c to all of them to be non-zero, as long as n is an integer greater or equal than 3. So later on, Breuil, Conrad, Diamond, and Taylor, they completed the proof of modularity of elliptic curves over the rational numbers. So once these results are established, it's a very natural question to ask, can we prove modularity of elliptic curves over, say, quadratic fields? And in that direction, the first results that appeared are due to Jarvis and Manoharmayun, who proved that semi-stable elliptic curves over q square root of 2 and q square root of 17 are modular. And again, this kind of results were motivated by Fermat equation, in this case, over the field q square root of 2. And this is also a theorem due to Jarvis and Mikin. They proved that basically Fermat's last theorem also holds over this field. In this case, now we take the exponent p to be at least 5. And around the same time, Jarvis and Manoharmayun proved this theorem. There is also another theorem that they proved back then, and that's more general. It's not for a specific field. So it's actually for any totally real number field in which 3 is unramified. And then there is also a condition on the elliptic curve, because now they demand that the elliptic curve E to have good supersingular reduction at the primes above 3. So if this is true, if this holds, then E is a modular elliptic curve over K. So now in this theorem, we have additional constraints on the curve, and this is mostly due to what kind of modularity lifting theorems were available at the time. So we're going to see that now we have much more general statements because we also have much stronger modularity lifting theorems. So following this philosophy of studying Fermat's last theorem over quadratic fields, myself and my colleague Samir Siksek, we have studied this Fermat equation over a variety of fields, and in particular, we have proved the following result. So for a set of real quadratic fields with density 5, 6, the asymptotic Fermat-Last theorem holds. So here by asymptotic, I mean that we need to allow the exponent p in the equation to be large. So it will be larger than some constant, and that constant will depend on the base field. But some of these results are also explicit. So in particular, when d is common to 3 mod 8, we know that Fermat-Last theorem asymptotically holds over that field q square root of d. I think Samir gave a talk about this kind of ideas 2 days ago. And again, he probably mentioned this, so essential to these ideas is to prove modularity of elliptic curves over the field that where we study the equation. And so motivated by this theorem, we proved together with Breuil Ang, we actually proved that all elliptic curves over real quadratic fields are modular. So these 2 theorems for us, they came in a package in a way. And nowadays, we will see later that the proof of this modularity theorem has been simplified for a variety of reasons due to progress that happened in the last 5 years, more or less. So we're going to see this today. So let's go back one step and say what we mean by modularity of an elliptic curve. So we're going to take k to be a totally real number field. So this will be a constant during this talk. K is a totally real number field. Gk will denote the absolute Galois group of k. And then E will be an elliptic curve over k. So we say that E is modular if there exists an Hilbert cuspidal eigenform f defined over k, parallel weight 2 with rational coefficients, such that the L function of E equals the L function of f. But in fact, it's also convenient, and we often think of modularity in terms of Galois representations. And so in that context, modularity means that there will be an isomorphism of compatible systems of Galois representations, rho EP. So this is the p-adic Galois representation arising on the elliptic curve E. And this must be isomorphic to the p-adic Galois representation arising in some Hilbert modular form. And this will then be true for all p. And finally, still an additional definition. So we're going to define what's a residual modularity. So in our context, we'll be considering the residual representation attached to the p-adic representation of elliptic curves. So this we denote by rho bar EP. And this representation, in fact, coincides with the action of the absolute Galois group of K in the p torsion of E. And we will say that this residual representation is modular if there exists an Hilbert cuspidal eigenform f over K of parallel weight 2 and some prime ideal lambda dividing P, such that the semi-simplification of the residual representations are isomorphic. So we take the representation arising in the p torsion of the elliptic curve, and on the other side we take the residual representation attached to f of the lambda adic representation attached to f. So in this, when this is true, we will say that the representation rho EP is residually modular. Okay, so now before we dig into the modularity of a totally real fields, let's first summarize the main steps of the proof of modularity over the rationals. because then we will basically generalize this proof and explain what are the challenges in each step. So the first step is to have available what is called a modularity lifting theorem. And this means that if we can show that we have residual modularity and additional conditions on the image of the residual representation, which will say it's big image or sufficiently large image, this should imply that the p-adic representation is modular. So the second step is a consequence of a theorem of Langland's tunnel. And basically it says that the mod 3 representation is modular when it's irreducible. So basically for p equals 3, this Langland's tunnel's theorem is allowing us to satisfy one of the hypotheses of a modularity lifting theorem. We already know that for residually modularity holds if the representation is irreducible. Finally, the third step is called the 3-5 modularity switching argument. And this is when we put together the first two steps to prove that the mod 5 representation is going to be modular when is irreducible or when the image is sufficiently large. So we kind of swap modularity from 3 into to modularity at 5. And finally, there is a final step, which is dealing with the exceptions. And this is actually the step that is more important when we move the field from Q to some totally real field. So the first three steps will tell us that an elliptic curve that is not modular is required to have image that is very small in a sense that we'll make precise soon, modulo P for P3 and also for P equals 5. So then what we have to do is to search for such elliptic curves. And we know, as we'll see, that the elliptic curves like this will give rise to rational points on certain modular curves. And then we enumerate those rational points. There should be just a few of them. And then for those we find, we need to justify that these elliptic curves are modular by some other reason, by other arguments. And then we have covered every elliptic curve. Okay, so let's go back to step 1 now. So what's a modularity lifting theorem? Well, modularity lifting theorem are often very technical and not easy to read at all. For example, here I'm showing you one theorem due to Breuil and Diamond that is very useful in improving modularity of elliptic curves over totally real fields. As you can see, that there's a long statement and many technical hypotheses.
When is this theorem?
I'm sorry?
When is this theorem?
This theorem is, I think, is published from 2013, 14 maybe.
I see.
And so this is just the hypothesis. And then the conclusion is also quite technical. So this theorem was proved by Breuil and Diamond, and it builds on the work of many mathematicians, including Kissin, Tobiji, Barnett Lamb, and Gerati. So the nice thing about elliptic curves is that when we make our representations of this theorem being replaced by what happens with elliptic curves, then the theorem becomes much cleaner. And in our case, it reads like this. So if E is an elliptic curve over a totally real number field K, and we take P to be a prime which is not 2, then if the mod P representation is known to be modular. So that's condition number 1, plus condition number 2. So the image of the Galois group of the field, the original field K, where we added the pth roots of unity, is absolutely irreducible. So if these two conditions are satisfied, then the curve is modular. So by what happens now is that having this theorem A available, then by the Langlands tunnel result and a 3-5 modularity switching, what we'll see is that we can prove modularity of the residual representation for P equals 3 and 5, and when the second condition of the theorem holds. Okay. And so that gives us the following consequence. So if E is an elliptic curve of a total real field K, if it has big image modulo P for P3 or P equals 5, then E is modular. Okay. So this is because we will be able to show that we have residual modularity, and then we are just adding the hypothesis that's the condition 2 in the previous theorem. Okay. Okay, so now, as I mentioned before, one of the important steps is to deal with the exceptions. So how do we classify these exceptions? And for that, we need to introduce just a few modular curves. And as the exceptions are going to be those curves that fail to satisfy the second condition of the modularity lifting theorem, that is, they fail to have the sufficiently large image. So we introduce the modular curves XBP, XSP, and XNSP to denote the modular curves parametrizing elliptic curves with image that are inside the Borel at P, or in the normalizer of the split Cartan at P, or the non-split Cartan at P. Okay, so what is well known about this residual image is the following proposition. So if E is an elliptic curve over K, totally real, and P is some prime, then the image of rho bar, which is the residual representation of P, of this Galois group that we want to be big, it's going to be equal to the intersection of the image of the whole absolute Galois group with SL2FP. And when this image is not big, by that we mean that the image is absolutely reducible, then the image of rho bar is contained either in the Borel subgroup, the normalizer of a Cartan subgroup. Therefore, this means that elliptic curve E gives rise to a non-cuspidal K point in one of these 3 modular curves. So if at this point we want to follow the same strategy as in the original proof over Q, we need to look for non-cuspidal real quadratic points on certain modular curves. For example, the modular curves that parameterize elliptic curves with reducible image simultaneously at 3 and 5. So that would mean looking for quadratic points in the modular curve X B3 and B5, which is the same as X naught 15. But some of the curves that appear, they have infinitely many real quadratic points, and we don't know how to prove modularity of these points all at once. So to circumvent this, what we're going to do is to introduce an additional modularity switching step. And now it's going to be 3-7 modularity switching. And this is an idea that appeared in the work of Manohar Mayuni. And analogously to the previous theorem for 3-5 modularity switching, what we can prove now is that given an elliptic curve over a total real field K, if the image mod 7 again of the restriction to K zeta 7 is absolutely irreducible, then the elliptic curve is modular. So putting it all together, we have the 3-5-7 switching argument, and we now know that given an elliptic curve E, if we have that the image is absolutely irreducible for some P where P is 3, 5, or 7. So this image here of the restriction to K of zeta P, if this is big enough, then the elliptic curve is modular. So what are the exceptions to this theorem? So this would mean an elliptic curve whose image modulo P for 3, 5, and 7 simultaneously is not sufficiently large. So in that case, it would give rise to a K point in 1 out of 27 modular curves that we can write down as X of U, V, W, now where U, V, and W belong to these sets, like it could be the Borel at 3, the Borel at 5, Borel at 7, or normalizer of split Cartan, or normalizer of non-split Cartan. For any of the possible 27 combinations, these curves have genus greater than 1, and so there are only finitely many K points on them due to a theorem of Faltings. And so we conclude already that fix the field K totally real, then all but except finitely many J invariants or K bar isomorphism class of elliptic curves over K are modular. So the challenge now is to restrict the field K to say degree 2 or degree 3, or as we'll see, and show that there are no exceptions in this statement. In fact, it's more than this is true, and in Bauli-Young PhD thesis, he proved that for every totally real field K, there exists only finitely many Q-bar isomorphism class of non-modular elliptic curves defined over all the totally real quadratic extensions of K. Not only defined over K, but one is allowed to consider the quadratic extensions as well. Okay, so at this stage, a possible route to proving modularity over quadratic fields is to try to enumerate all non-custal real quadratic points on these 27 modular curves, and then prove that the resulting points are modular. But this is a really huge task, and most of the curves we won't be able to do this. So instead, what we do is to look more carefully at what can be the possible images of these elliptic curves modulo 3, 5, and 7. So after looking more carefully, it's not too hard to prove the following more detailed proposition. But we do need an additional hypothesis here, is that we take P to be a rational prime such that the intersection of our base field K with the cyclotomic field of Pth root of unities is Q. Okay, so then we suppose that our residual representation mod P is irreducible, but the image of the restriction of GK zeta P is not sufficiently large, so it is absolutely reducible. Then we can show that for p equals 3, the image of the mod 3 representation is conjugate to the normalizer of the split Cartan subgroup. And in this case, it has order 8, and the projective image is isomorphic to Z2 times Z2. For p equals 5, one can be quite explicit also about the image, so it would be conjugate to the following group H generated by these two matrices, that is order 16, and what's important to us is that this is a subgroup with index 2 inside the normalizer of the split Cartan subgroup, and it can also be seen as of index 3 in the normalizer of the non-split Cartan subgroup. And finally, and more important of all, is for p equals 7. So for p equals 7, one can show that there are two possibilities. So there are two subgroups, H1, H2, generated by these explicit matrices. H1 has order 36, contained with index 2 in the normalizer of split Cartan subgroup. And H2 has order 48 and is contained in the index 2 in the normalizer of a non-split Cartan subgroup. And we can also describe the projective images. So in view of this proposition, we introduce a couple more modular curves. So now for these groups H1 and H2, specified in this part C, we'll denote the modular curves corresponding to these groups, X of H1 and X of H2 by XD7 and XE7. Okay, so as a corollary of this new description, if we take K to be a real quadratic field and E some elliptic curve over K, then what can we say? So if the image mod 3 is not sufficiently large, so again, this restriction to this field, the Galois group of this field is absolutely reducible, then E will give rise to a non-cuspidal K point in XB3 or XS3. Now for p equals 5, we need this additional hypothesis that the quadratic field is not Q square root of 5, because we remember we need the intersection with the cyclotomic group, the field to be Q. So in that case, we would get a non-cuspidal K point in XB5 or XS5. And finally, for p equals 7, if the image is not large enough, then we will get a non-cuspidal K point in XB7 or XD7 or XE7. Why is this an improvement compared to the previous description? So note that, okay, so this is just a comment about the part B, because here in part B I write X of S5, but we actually had a more specific description. If you remember, we had this specific group X of H, and we are not using XH because in practice, everything we calculate later on works simpler with X of S5, but the reality is that we could have replaced in the corollary X of S5 with XH. Now, a second comment is that parts A and B, they do eliminate some modular curves. They eliminate the modular curve X NS3 and X NS5. And finally, just observing that why is the condition K not equal to Q square root of 5 necessary? Because indeed, if we consider this field, then the determinant won't be surjective. And this will give rise to more subgroups of GL2 of F5 of order 6 and 8 and 12. And one of these subgroups is contained in the normalizer of a split Cartan subgroup, but not in the normalizer of the non-split Cartan subgroup. While the other end, the subgroups of order 6 and 12 are contained in the normalizer of a non-split Cartan, but not in the normalizer of the split Cartan. And so we would have to consider more cases. Okay, so we have built up to the following conclusion now. Modularity of real quadratic fields will follow from the following two results. The first one is that all elliptic curves over Q square root of 5 are modular. And the second is that all non-cuspal real quadratic points on these 7 modular curves correspond to modular elliptic curves. Finally, just for completeness, the proof of this lemma relies on the following theorem that says that if we have an elliptic curve over a real quadratic field that is a Q curve or SEM, then we know that it is modular. So let's.
Whose result is this? The last theorem?
Sorry?
The last theorem, when E is either Q curve has a CM, then it's modular over K. So where can we, what's the reference?
A difference between what? Sorry?
No, can you quote the reference for the last theorem?
So this theorem is a classical result. It's not part of what we proved.
And who did this? I mean, who proved this, or is it easy to show this theorem?
Oh, who proved it? So I think the CM case is quite old due to maybe Eck.
Mm-hmm.
And the Q curves, I think Ellenberg proved and Rivet proved the modularity of Q curves, at least back in the day, assuming Serre's conjecture, but now Serre's conjecture is a theorem.
Okay, yeah, thank you.
Okay, so this let's just go briefly over the proof of the proposition, because it's important to avoid this field later on, and it's kind of short. Okay, so we're gonna know, as before, we can assume that we have a small image, so the image is simultaneously absolutely reducible for p equals 3 and 7, because otherwise modularity lifting theorems tell us that the curve are modular. Okay, so then this gives rise to a k point in one of the following 4 modular curves. So the image at 7, what can it be? We had 3 possibilities for it. It was either inside the group H1, H2, or the Borel. So that gives rise to a k point in XD7 or XE7, and also XB7. But for the case of mod 7 reducible representation, we also consider information coming from 3. And what can happen at 3? Well, it's either the image is either in the Borel or in the normalizer of a non-split Cartan. So we have these 4 curves, and it happens that the first 3 curves are isomorphic over Q to the elliptic curves 49A3, 49A4, and 21A1. All of them satisfy that so the k points are equal to the rational points, and so all the k points are modular. Finally, the last curve can be described as the quotient of x naught 63 by Atkin-Lehner involution. sorry. And by taking the quotient by the involution at 7, we obtain again the curve 21A1, which we already know to satisfy that the k points are rational. So if we start with some point k point in xk, the image in y will be in yq. So we can consider some point p and its conjugate p sigma. So sigma is the non-trivial element in the Galois group of q square root of 5 over q. And these 2 points need to map to the in y to the same point. So if they map to the same point in y, from this description of y, we see that either p sigma equals p or p sigma equals W7 of p. In the first case, p is a rational point, or in the second case, it corresponds to a q curve, and so it is modular in both cases. So we're done with the proposition. There's still a lemma, and the lemma says that we need to control the real quadratic points on 7 modular curves. But these modular curves are of I genus, and this is a difficult task. But due to the latest developments in modularity lifting, this task is now outdated. So this is due to modularity lifting theorems established by Thorne and Kalyan-Swamy. So instead of trying to pursue that task, let's see what new information we get out of the latest modularity lifting theorems. So again, Thorne proved some modularity lifting theorem that is a technical statement, but when we replace everything by elliptic curves, it becomes simpler. And in that case, we get this theorem. So if E is an elliptic curve over total real field K, and at least one of the following 2 conditions hold. So either the mod 3 representation as large image, or the mod 5 representation is irreducible and skew root of 5 does not belong to K, then the curve is modular.
This theorem of Thorne actually replaces the previous theorem of Breuil and Conrad, or there are certain different applications.
It covers an additional case.
I see.
Yes. So in view of this theorem, one concludes the following. So Thorne writes down the following lemma. So if K is a total real field not containing square root of 5, then any elliptic curve which is non-modular over this field gives rise to a K point in X B3 B5 or X S3 B5, right? Because it's non-modular needs to, both conditions need to fail. So the first condition failing means that the image is either in B3 or in B5, and the second in B3 or S3, and the second condition would give us reducible image modulo 5, and so we always have B5. And then there's a second part of this lemma that says, given a cyclic number field, if the K points on these curves are the same as the rational points, then all elliptic curves over K are modular. Now, based on this, he proved in modularity of elliptic curves over the cyclotomic ZP extensions of Q. And the way the proof works, just a summary of the proof, because it's not, it's a very nice proof using Iwasawa theory. So we know that the elliptic curves that one has to consider, the modular curves that one has to consider, are isomorphic to elliptic curves 15A1 and 15A3. And then Thorne shows that these specific elliptic curves satisfy that the k points are rational points, and so we are in the context of part 2 of the lemma, and so the elliptic curves are all modular. So that's one consequence of one more modularity lifting theorem. But then we have an additional modularity lifting theorem that appeared more recently, and that is the following. So this one now works for p equals 7. Again, we need this condition that the first condition, intersection of our field K with the cyclotomic field, the 7th cyclotomic field must be Q. The mod 7 representation is irreducible, and moreover, the image of the mod 7 representation is not conjugate to a subgroup of the normalizer of the non-split Cartan modulo 7. So if this holds, then the curve E over K is modular. So making use of all this technology, Martin, Derek, Philip Nyman, and Samir Siksek, they prove that all elliptic curves over real cubic fields are modular. So the proof of this goes by first considering one specific field separately. So in this case is the total real part of the cyclotomic field of the 7th roots of unity. So they first prove that all elliptic curves over that field are modular. Under that hypothesis, then we can assume that the intersection of K with the cyclotomic field of 7th roots of unity is Q. And so if the elliptic curve is non-modular, because the field is cubic, we know also that square root of 5 does not belong to K. Then by the theorem of Thorne, the mod 5 representation needs to be reducible. And by this newest mod 7 modularity lifting theorem, we have that the image mod 7 is either in the normalizer of the non-split Cartan or in the Borel. This gives rise to so this gives rise to a point in two modular curves, which I notice here that this must be wrong. So because I'm not, that there should be, instead of B5 in these curves, one should see B7 and NS7. We are using the latest theorem modulo 7, so one needs to use the image at 7 in these modular curves. And once this has been proved, then the authors do quite challenging computations to compute the K points in these curves and show that everything is modular over cubic fields. Finally, we also have modularity over quartic fields. And now that was proved recently by Joshua Box. But before I state the theorem, let's just say that everything that was said until now applies with the more general totally real number field K of any degree, as long as the intersection of the field with Q square root of 5 is Q, and with the cyclotomic field of 7 roots of unity is also Q. In this case, if we have some elliptic curve that's not modular, then it must give rise to a K point in one of the following 4 modular curves. So you see now we started with 27 curves, went down to 12, then down to 7, and now it's down to 4. But these curves are still complicated. The genus is I. But Joshua Box, in his incredible PhD thesis, he applies a variety of methods and determines all real quadratic points, real quartic points on these curves over fields that do not contain square root of 5. And it proved that if K is a quartic totally real field such that square root of 5 is not in K, then all elliptic curves over K are modular. Okay, so let's go back now, after all this additional technology, to the case of real quadratic fields. Now, this is just a corollary of everything I've said. So first step in the proof is elliptic curves over Q square root of 5 are modular. We already saw this, so we can assume K is not Q square root of 5. Now, from the previous slide, we know that if E is not modular, then E gives rise to a K point in one of the following 4 modular curves. But we can see that if we forget the information at 3, we get B5, B7, and that's X naught of 35. And if you remember that the groups E7 is actually a subgroup of the normalizer of the non-split Cartan subgroup, then we forgetting again the information at 3, we also get a point on XB5 and S7. Finally, quadratic points on X naught of 35, they've been computed and they correspond to elliptic curves with CM or Q curves, which we know they are modular. And finally, this final curve comes out of the wash in Joshua Bock's work, that the quadratic points in this modular curve XB5 and S7 also correspond to elliptic curves with CM and Q curves. And in both, I mean, in any case, in these computations that are involved to conclude that the points are CM or are Q curves, these are fairly easy compared to the calculations that one had to do previously before all these new modularity lifting results. So this is a much shorter proof of modularity curves over real quadratic fields. Okay, so let me just remind of all the results we have seen in a single slide. So we have proved that fix the field K, there are only finitely many J invariants corresponding to non-modular elliptic curves. And if the K is real quadratic, then all elliptic curves of K are modular. Then Jack Thorne proved that all elliptic curves contained in the cyclotomic ZP extension of Q are modular, and for all P. Then Derek, Nyman, and Sixek, they have proved that elliptic curves of real cubic fields are modular. And finally, Box showed that all elliptic curves of real quartic fields where square root of 5 is not in the base field are modular. So the next step is degree 5, and I've seen a paper on arXiv. So there's a preprint that says that for all but finitely many degree 5 totally real fields, so there's a finite list of degree 5 totally real fields such that for every other degree 5 totally real field K, the elliptic curves defined over those fields are modular. So this appeared, I think, about 1 year ago, more or less. Okay, so this kind of finishes the overview, and I still have 10 minutes, so I want to say a little bit about the 3-5 modularity switching theorem and how does that work, because all these methods that one needs to compute these quadratic points or cubic points, or these methods evolve. The curves that one is to consider also evolve according to the modularity lifting theorems that we have available. But on the back of all of that is the 3-5 modularity switching theorem that is common to all of this. Okay, so let's have a look at that. And the idea is that one starts with modularity modulo 3, and then one can kind of propagate modularity into 5, starting from the model 3 modularity. So the model 3 modularity is what we would say that's the seed of modularity, and it is a consequence of a theorem of Langland's tunnel. So there is this classical result that says that if we have a representation from the absolute Galois group of a totally real field K that is odd, irreducible, and finite solvable image, then there will be a Hilbert modular form of parallel weight 1 such that the L functions of the representation and the modular form coincide up to finitely many Euler factors. And a corollary of this is that if we start with an elliptic curve E over K and the mod 3 representation is irreducible, then the mod 3 representation is modular. And if we put this together with modularity lifting, then if the mod 3 representation is as image which is sufficiently large, then the elliptic curve is modular. Okay. So part 2 of this corollary follows from part 1 and modularity lifting. Now, part 1, to prove part 1, one first starts with the following observation. We can find a representation I of GL2 of F3 into GL2 of Z with square root of -2, and we can see this as a complex valued representation. And it's also possible to assume that modulo this ideal, which is an ideal above 3, we get the identity. So we can apply the theorem of Langland's tunnel to the composition I composed with our representation rho bar. Okay, so this is a complex value, and it will satisfy, because of it's coming from an elliptic curve, it will be totally odd, absolutely reducible by assumption, and the image is finite and solvable, and so satisfies the hypothesis of Langland's tunnel. So we can find some Hilbert modular form associated with this representation, and it will have parallel weight 1 and eigenvalues in this field, in this ring. On the other hand, there is a lemma on one of the papers of Wiles that says that we can find an Hilbert modular from theta of parallel weight some power of 2 trivial character such that modulo 3 it coincides with 1. And now we can multiply these two things. We multiply theta by f1, and now we get something of weight w, which is 2 to the I plus 1 plus 1. And modulo 3, it is congruent with f1. So the product theta f1 modulo any prime dividing 3 is actually an eigenform modulo that prime. And so there is a lemma of the Linser that allows us to say, well, then we can find a eigenform fw of parallel weight w such that the residual representations all coincide. Now the only thing left is to replace this fw by something that has weight parallel weight 2, and this is also something that it's known that it's possible to find some weight to form. Maybe the level needs to change such that residually we have the same representation. Okay, so this proves this modularity, the seed of modularity modulo 3. So now we have the 3-5 modularity switching argument. And the idea is that given some elliptic curve E over K, we'll be able to find another elliptic curve E dash, also defined over K, such that the mod 5 representations of the two curves are isomorphic. And this new curve E dash has large image modulo 3. So as a consequence of this, we have that if our elliptic curve has large image modulo 5, then it is modular. And the proof goes like this. We take E and E dash as in the lemma. And by our assumption 2 in this lemma, we know that E dash is modular due to its mod 3 representation. So if E dash is modular, all representations attached to E dash are modular. In particular, the 5-adic one is modular, and so we can reduce the 5-adic representation and conclude that our original elliptic curve also has a 5-adic representation, a residual mod 5 representation that is modular. So and now, because we have the assumption that the image mod 5 is sufficiently large, we can again apply modularity lifting at p equals 5, and this gives us that E is also modular. So to finalize, I'll just summarize the proof of the lemma. Okay. In order to prove this lemma, we need to use another modular curve. So this is the modular curve xe of 5 that parameterizes elliptic curves E dash with a symplectic isomorphism between the 5 torsion of E dash to our fixed elliptic curve E. And by symplectic, I mean that the veil pairing is preserved. So the important property is that xe of 5 is P1 over K. So because over K var, it is isomorphic to it's a twist of X5, and so it's smooth of genus 0 over K, and it has a K point because we can take E as a point. Finally, the description, more precise description of these points is that its non-custal K point in xe of 5 correspond to classes of pairs when we have an elliptic curve E dash, and in the first part of the pair, and the second is a symplectic isomorphism of the 5 torsion as a GK modulus. And these two pairs are isomorphic, so they belong to the same class if the K isomorphism, there exists a K isomorphism that maps the E1 dash into E2 dash such that U2 is obtained from U1 by composing with this isomorphism 5. Okay, so now to the proof of the lemma. Any K point on xe of 5 will give rise to an elliptic curve E dash satisfying condition 1. That means that we have an isomorphism of the 5 torsion between E dash and E. And we also want that our point satisfies condition 2. That was a condition modulo 3. So modulo 3, the maximal subgroups of GL2F3 are SL2F3, Borel subgroups, and normalizer of the non-split Cartan subgroup. So if the image is not large enough, then we know that our point will correspond to an elliptic curve E dash that gives rise to a point on the following fiber products. So xe of 5, maybe the image model 3 is reducible, so that would be fiber product xb3, or maybe the image is in the normalizer of the Cartan, in which case is this second fiber product. So these fiber products are isomorphic over, so over C, the normalization of these two fiber products are isomorphic to all the modular curves that we have seen before, so X5 B3 and X5 NS3, and so these are irreducible. And now that we know this, we apply Hilbert's irreducibility theorem to conclude that there will be some point K in Xe of 5 that does not lift to a K point in neither of these two fiber products. So in that case, that means that the mod3 representation of E dash is large enough. Okay, so I think this is a good place to stop. The time run out of time, but it's a nice place to stop. So thank you.
Yeah, thank you, Dr. Nuno Freitas. So are there any questions or comments or any clarifications required? Please feel free to ask. Please unmute and you can ask.
No, are there the modular parameterization version of any of the modularity result you quoted?
I'm sorry, can you repeat the question?
Can we state those result of modularity in terms of modular parameterizations?
You want to
morphism over Q over the concerned number field from modular curve to elliptic curve in that way?
I'm sorry, I can't understand.
So the classical modularity result can be stated in the modular parameterization by a morphism from the both curves.
Oh, so over
Q, yeah.
Over Q, you have several equivalent modular ways of modularity, but over a total real field, it's not always possible.
Okay, so any of the results that you quoted not possible? None of?
So I'm sorry, I can't hear you.
You stated 3/4 theorems, right? By modularity. So it is not possible for any of the result?
So these theorems here?
Yeah, I'm asking these theorems. So they cannot be stated means they're not equivalent versions?
I'm not sure, but I don't think so.
Okay. Okay, thanks.
Yeah, I have like one or two questions. So you have looked at various modular curves. How difficult or easy to compute their genus?
I think the genus of these ones that we used, they were computed.
Yeah, like for example, here 31, 13, 21, etc. you are writing. So how does one compute this?
We did this with some, well, there's a formula, forgot the name of the formula.
Hurewicz formula?
Yes. Yeah, Riemann
Hurewicz. Yes, Riemann Hurewicz.
It's, if I remember, this was calculated, maybe not all the cases, but many of them we using that formula.
I see. Okay. And just one more question. So in many of these cases, when you looked at either quadratic points or cubic points, kind of they turned out to be points on the rationals, Q rational points, and from there we were able to say whether it's modular or not. So are there any genuine cases where the points are not turned out to be defined over Q, but they're genuinely points which are defined over say quadratic field or a cubic field? So is there any such situation happened in any of these proofs?
Yeah, so yes, so I can't, here we have, when were working with one of these 7 curves, there is at least one of them that yields points that are Q curves, CM, and maybe 2 more additional points that are not CM or Q curves, and one then needs to prove they are modular by some other reason. Yes.
Okay.
I think that we still managed to show that the image was large, say modulo 5 or modulo 3, and then conclude again by modularity, the same modularity lifting argument. I think that's something like that happened in one.
In another case. I see. And I mean, I do understand that the reason for having totally real number fields is because you want to apply modularity lifting theorems at several places. But suppose you genuinely starts with an imaginary quadratic field or some imaginary field. So typically, like, is there any other method one would think of to solve these equations? I mean, solve these problems?
So over imaginary quadratic fields,
yeah.
So there's been recent progress, the work of many authors. There's a paper proving modularity of many elliptic curves over quadratic imaginary fields. But I don't really know how those methods work. What I understand is that we don't have this seed for mod3 modularity that I discussed here in the end, so it's not, one cannot do this argument here. So the residual modularity modulo 3 does not work over imaginary quadratic fields. So we miss this seed for modularity. And so they need to do this with a completely different idea, but I don't know how it works.
And maybe one more question I had was, like, one of the case that when K over Q is cyclic, I think in one of the Thorne's theorem, I think. Yeah, here you say that if K over Q is cyclic, then the K rational points, in fact, corresponds to something like yeah, so this theorem. So I mean, somehow, yeah, I mean, like, where do we use cyclic in the sense, like, I mean, I'm just wondering how cyclic K over Q being cyclic would be useful.
Yeah, for the second part of the lemma, right?
Yeah, second part of the lemma, yes.
So it's useful because you get modularity over Q, and then you cyclic base change gives you modularity over K.
Oh, cyclic base change, you want to use that. Okay. Yeah, maybe one last question. So in the last slide, you said there are two curves and they are irreducible, right?
Yeah.
Like x5 b3 and x5 ns3. So why are they irreducible?
So these curves are defined as I mean here, right? So we have these fiber products, and they are over the complex number. The normalization of these two curves are isomorphic to these modular curves.
Right.
And because these are modular curves, these will correspond to irreducible curves, because we have some congruent subgroup acting on the upper half plane, and this gives a connected Riemann surface.
Okay. Okay, fine. Okay, yeah, thank you. Thank you, Nuno Freitas. So are there any more questions, comments from anyone else?
Yes, I have one question. You have talked about Q curves are modular. So I was wondering, can we get some conditions when Q curves are basins of some elliptic curves defined over some lower field? So is there some conditions like that when a Q curves become a elliptic curve? Suppose some are quadratic also.
So you're asking if, given a Q curve, one can tell if there is a smaller field and another elliptic curve that obtains the Q curve by base change?
Base change or some isogenous, it becomes isogenous to the given Q curve.
I don't know if there is a condition like that.
Okay.
Hello, I have a question. It was suggested by the last question. Take K, for instance, a quadratic field. So you've proved modularity of elliptic curves over K. Now, what about the modularity of K curves, where a K curve would be a curve over Q bar, which is isogenously to all its conjugates over K.
So K would be a quadratic field, I mean.
Let's say, I mean, of course, the question could be completely general, but let's say a quadratic field just to start, because the problem might be very hard.
Yeah, so you would say there's some curve over, let's say, a quartic field that is a K curve over a K quadratic field, something like that.
Yeah, well, just say the concept of Q curve is clear. So K curve is analogous.
So I think that the proof for Q curves relies on Serre's conjecture.
Right. That's the original proof by Ribbit.
Yes. So having modularity of K curves would maybe require also some powerful theorems over K. Not enough the modularity of elliptic curves. So, so I don't know that. I think the answer is that we don't know modularity of K curves over quadratic for K quadratic. So is that what you were asking?
Yeah, that's exactly what I was asking.
So I don't know
whether any of the methods that you have would start going in that direction. The other question I would have is, it felt as if there are really powerful results that have been proved, and I'm just wondering whether that last result that you mentioned about over for quantic fields might apply more generally, that there would be only a finite number of fields which would be extremely hard of a given degree, right? If you take totally real field of a degree D, that maybe D has to be a prime, I don't know, but certainly that would make it easier. But consider all fields of degree D, that there might be only a finite number of fields over which you would have problems proving modularity of elliptic curves over that field.
And yes, the authors of that in the preprint, they discuss that. They have a couple of remarks about precisely that, and they say that something like that the method should go through if you replace 5 by some prime with, and they point out where there might be a challenge, but it seems that they have. It sounds like they are open. There's hope, but that's all I know about that. Is what I've read in that paper.
So this is on Archive?
Yes, the papers
the
on
paper
Archive.
that you mentioned? Yeah.
Let me, I can show you the authors again. Probably the title is Modularity of Elliptic Curves over 5 degree 5.
Okay, I guess Ito is the easiest name to remember, so I'll look for him in Archive. Thank you. Lovely talk. I wasn't aware of all these modularity results.
Yeah, thank you. Are there any more questions?
Oh, thank you.
Thank you. Welcome.
Yeah, are there any more questions or comments?
Professor Kumar was commenting something. You can complete. Professor Kumar?
Yeah, it's complete.
Okay, thanks.
Okay.
Yeah. Oh.
No, Dr. Devendra wanted to know if your question is complete. Okay. Otherwise, please unmute and thank the speaker. Thank you, Dr. Nuno Freitas. It was very nice talk.
Exhaustive talk. Yeah. Thanks.
Thank you. Thank you.
Thanks, Narasimha, for chairing also.
Yeah. Okay. Thank
Thanks,
you.
Nuno.